he has to be able to do this step. If you understand my meaning without me writing too much more. In other words, can you pass the differentiation inside? Can you commute the order of differentiation in summation? Is that an allowed step of calculus? In fact, no, not generally speaking. It's not possible to do that. So like, here's the cautionary tale. In fact, generally speaking, it is not the case that d dx of the sum of Cn un is not generally equal to the sum over Cn dun dx. In fact, this is caution. You need some extra data about the series in order to make that happen. All right? And the counterexample that he gives, all right? The counterexample he gives, something you cannot differentiate term by term. You know what it is? It's exactly the one we differentiated last time and got confused about.
Well, that's convenient.
Yes. It's that guy. If you differentiate this, right? Like, just go willy-nilly and do it. Like, you can do it. Like, pretend you can. And this is, again, not legit. The FDX is, so just bring, you know, sum over ddx of the stuff, right? What's that give you? As we worked out last time, the L and the N and the pi, they cancel. And you're left with sum n equals 1 to infinity, you know, minus 1 to the n plus 1. There's a 2 cosine, right? We go from having something which is convergent, right? You can compare this to the alternating harmonic series, for example. Show that it converges. And then this is not convergent. So we differentiate, and it's not just like it's not, I mean, it's really bad. It's not like it just fails at some endpoints or something either.
And just go up and down and up and down and up and down, right?
It fails everywhere. There's no x for which this series converges. The nth term test, right? You look at the nth term, it doesn't go to 0. Fails by the nth term test for arbitrary x. So by doing term-by-term differentiation of this Fourier series, we're not like a little bit off. It's completely bonkers. It's just garbage. Why is that? What makes this calculation fail, as we'll see, is ultimately the lack of continuity in the Fourier sine expansion. That's the source of this somehow. All right? I haven't shown that yet. But in fact, we stumbled upon the standard example of why you can't just, you know, just go on your merry way and just calculate anything with Fourier series with careless abandon. In fact, Fourier series, so you start to appreciate why it is. Fourier series is one of the things that really ushered in the careful analysis that you're forced to take. I mean, that you love. Your real analysis course and so forth, right? Epsilons and deltas and all that. A lot of this work in the 19th century, Cauchy, Weierstrass, others, was a response to this sort of madcap, freewheeling garbage, I mean, good stuff, by Fourier that, you know, he's like, oh, you can write any function as a sum of sines and cosines, right? And like, if you're somebody like Euler, or, you know, you're sufficiently clever, you understand that this doesn't mean you made a mistake. It means that you did something. I mean, you understand where you can't do it, right? But it's a little bit subtle where you can't do it. And actually, the analysis of the problem is necessary to make correct calculations. So it's a place where analysis is actually not just sort of legalism. It's necessary for good living. That's right. I forgot. You guys may be fundamental independent Baptist types. I don't know. It's here.
See, I thought that was a theological comment, but I
Let's see
wasn't
here.
positive.
Fourier. So is that a microaggression? Was it a medium-sized aggression? I don't know what kind of
Wait,
aggression.
so are you legalist or not legalist?
I think everyone says that they're not legalist, right? A Fourier series that is continuous. Legalism's not cool anymore, right? Fourier series that is continuous can be differentiated term by term. Here, truth. A Fourier series that is continuous can be differentiated term by term if f prime of x is piecewise smooth. Right? He says the result of term by term differentiation is the Fourier series of f prime of x. Right? Which may not be continuous, but it has to be piecewise smooth.
The function itself does.
Yeah. Let's see here. Fourier cosine series. If f prime of x is piecewise smooth, then a continuous Fourier cosine series of f of x can be differentiated term by term. The result of term by term differentiation is that the Fourier sine series of f prime of x may not be continuous, right? Because we don't necessarily have that f of L is equal to f of minus L. All right. So let's look at this here. Let's take this out first. Then what happens when we differentiate? So I can get rid of this thing because it's not behaving well. I guess I can work over here actually. I've erased it. But the point of this was, for our initial condition function, right? What do we have for it? U of 0 equals to U of L equals to 0. Right? Or more to the point, U of 0 was equal to U of L. And then basically what we did was found the Fourier sine series for that function, for the initial condition function. All right, well that's exactly the one, that's okay. It can be differentiated term by term because it's continuous. It meets the conditions needed for the term by term differentiation theorem, which is why those steps are legitimate.
And that was how we tested its accuracy, right? When we did that, when we like plugged it back in and checked it, we had to differentiate it, didn't we?
Yeah, I don't know how careful we were when we did the earlier things. I don't think we... Basically, I structured the calculation in such a way that we couldn't get into trouble. And I probably hid some of the mathematics here with physical assumptions in our earlier first 3 talks. But getting to the point. So this guy, right? We have x equals to, what was it, L over 2 minus the sum. What happens if you differentiate this? Can we differentiate this Fourier cosine series?
Yes.
Right.
F of negative L is equal to F of L.
K plus 1. So you differentiate this. If this is f of x, right? This is f prime of x. Certainly piecewise continuous, right? Therefore this, which is going to, the minus, right? Oh, right. L's cancel, don't they? We're left up with 4 over 2k plus 1 pi, right? Because this one cancels with one of them. The minus from the cosine cancels with this minus. The L's swap out, and you got yourself a sine of 2k plus 1 pi x over L. So the derivative of a cosine series give us a sine series. Now this is certainly not continuous, right? But it's piecewise continuous.
And it converges.
Right, yeah, so we got like, it's one of these guys. And I think it's, I want to say it's this, right? The derivative of even is odd. So I think this is what happens. But the point is that this is still okay. I mean, this is a convergent series, at least for some, for many points. Maybe all points. Let's think of that. It's not easy to show that this is, I don't think it's that easy to show that that's convergent directly, though. This is a tough Calc 2 problem to show that that actually converges. It looks almost, it's right on the bubble of being harmonic, you know? It's like 1 over is a reciprocal times a sine. I forget how to show this one as convergent, but at the moment. Oh no, don't tell my Calc 2 students. Oh no. Alright, now, he writes it a little bit differently in equation 3.47. So this is Haberman's 3.4.7 basically, but he writes it in terms. He just has a summation. He writes n odd, which is probably smart. Not that smart. Let's see here. So then what? And then he says it's correct. All right, very good. All right, well, I'm glad you said it's correct. Oh man, that is the, well, that's just the worst. All right, so next time I will prove this theorem. If f prime of x is piecewise smooth, then the Fourier series of a continuous function f of x can only be differentiated term by term if f of 0 equals 0 and f of L is equal to 0. So it's actually better than that. In the process of the proof, we'll find that in the absence of this condition, there is still a differentiation term by term theorem, but there's just some extra baggage that comes along. Like you can't differentiate term by term, but you can do something kind of related. So it's that's on page 117 of Haberman, and so that hopefully I'll prove that theorem. The proof does not look particularly difficult, and so we'll do that, and then hopefully we'll talk about. I want to talk about Parseval's equation and a little bit more on the orthogonality stuff, and hopefully the complex form of a Fourier series. I think that might be a little bit clearer. The complex form of a Fourier series. His heart's not in it, but I may skip over here to Weinberger. In Weinberger's, I noticed it looks like he commits to the complex method, and he proves, he's got section 15, orthogonality and least square approximations, and in there, like, he does a lot of the mathematics of what we're doing, and in a few pages, it seems like he has derived most of the results that we're interested in some sense or another. Maybe it's more pages than I can cover. I don't know. I'm going to try to pick some things from Weinberg. We should also be reading Weinberg pages, basically. Let's see here. I'm not sure about change of scale. I don't know if that matters or not to us, but basically sections 15 through 20, which is like pages 70 to 87 in Weinberger. That's where he talks about the mathematics that we're fussing with at the moment. So anyway, hopefully I'll do that, and then after next time we should have what we need for the Fourier mathematics for a while anyway. There is a larger discussion of the Sturm-Liouville problem and the eigenfunction expansions and so forth that we should get back to later, along with the Green's functions, but that can come later. So.
Green's functions is